information that uses, we can take in information for a number of scales over the image when we actually work this out. So the solution to this that we use is as I mentioned earlier on, build a classifier that tries to say, given an input image patch, can you tell us whether the pixel at the center of this is a boundary or isn't a boundary? So I don't know how many people have seen a plot like this before. Okay, so this is your sort of classic machine learning classification plot where you've got two kind of input features. So these could be the values of two neighboring pixels. And then here you've got all your kind of examples for where these two pixels represent a boundary, and all the examples for where they don't represent a boundary. And you're generally trying to find a straight line. Most of machine learning is really just finding straight lines, just really elaborate straight lines. You're trying to find the right straight line that separates these two classes apart. So in this case, this kind of patch here with the corner of the box in its place, that we want to find as a boundary. The one in the middle of the wall we want to find as a not boundary. So the kind of the favourite technique of this nowadays is using a convolutional neural network. How many have heard of convolutional neural networks? Okay, about the same number. So these are kind of, you're familiar with deep learning, at least you've heard of this term. So convolutional neural networks are a form of deep learning model, and what they basically do is they will learn increasingly rich sets of features to allow you to make really kind of expressive models where you just give this model an image as an input, and it can give you an answer as the output. So if you wanted to do, say, the classic is recognizing in handwritten digits for, passing postcodes or something like that. You give it loads of images of digits, and then you give it the actual digit that image contains, and these models can automatically learn just from taking the raw image to tell you what digit it is at the end. So we employ the same principle here, in that we will take loads of images of people's rooms, and then we'll have images where we've marked on the boundaries of those in between all the objects that we're interested in. When I say we've done some of them, but we pull in data anywhere we can find data that has this, because it's very expensive to do. It probably takes you 3 minutes to do a single image, and we need hundreds of them. So thousands would be lovely if we could get hold of them. So we basically give it loads of examples of people's images, of people's rooms. We then go and give it the boundaries, and then these models are able to automatically learn from that. You put the image in, and it spits the boundary image out at the other end. It's incredibly convenient. So yeah, this is the kind of main principle, and this is sort of an illustration of how a convolutional neural network works, in that you take each kind of layer of the network has what's called a receptive field. So this is a part of the image that it's sensitive to, and it runs what's called a convolutional kernel over it. So this is how many people are familiar with convolutions? You need to go and study signal processing. It's a fascinating subject. So like how, for example, when you have your treble knob on a hi-fi, if it's a digital treble knob, it works in the same principle, where you learn a filter, and you can pass that filter over your audio signal, and it has some effect on it. So hi-fis have treble and bass knobs, and they work using the same principles as how these work. So at each layer we basically learn lots of these filters. So just like a treble filter, but it processes an image. So it might enhance edges, or it might enhance corners. Google have done some really interesting things where they go and work out what features an image these convolutional neural networks like to find, and then they can generate new kind of crazy images from them. But basically you stack all these up, so it's like stacking the treble knobs on your hi-fi, until eventually you can then build something that right at the end goes back to our straight line problem. So all this really does is an elaborate way of turning data where there's no straight line to separate them into data where you can separate it with a straight line, and then it fits the straight line at the end and tells you which side of the straight line it sits on. It's really interesting to learn about, should you have the time with the information. So that's that. So putting that together, so we take our geometry that we estimated by looking for the vanishing points using a sort of a generative statistical technique. We then find the image segmentation that we use the boundary classifiers for. And then the application is, okay, so now we essentially draw a virtual room over our photograph. When there's no objects in it, you can't see the room. As soon as you click a wallpaper on, we're then basically drawing a wallpaper onto the wall of our virtual room. And we do some clever stuff using the image underneath in terms to relight that wallpaper. So we take the lighting information from our original photograph and extract the kind of the brightness of each region and use that to apply to the wallpaper to give it a kind of convincing look so that you can see the same contours from the underlying image. And then that gives us this. We're just literally drawing our virtual room over the top of our photograph. So yeah, that's that really. So now we'll just talk a bit more about what our kind of future roadmap is and the kind of directions that we're interested in exploring. We are recruiting at the moment, so if anybody's interested in these kind of things and has a good background, come and talk to me afterwards. So our next kind of thing we're looking at now is going into sort of full 3D. So this photograph stuff's great because you can take a picture. Any consumer has a mobile phone, it's got a smartphone in it. Anyone can take a picture. Anyone can use this within kind of 10 seconds is what we're aiming for. We're now interested in, okay, but there's also limitations in that, and that we're always going to be stuck with sometimes it's going to go wrong. There's certain rooms that we just won't be able to manage because of the limitations of a single photograph. So we're looking at how we can use things like, say, like the Google Tango device and the Intel RealSense devices. So I don't know how many here are familiar with Tango and RealSense and occipital cameras. Not many. Okay, so yeah, there's like two, and one of them works for us. So the basic principle of these are like really clever, like special smartphones, and they've got a camera in them that works just like the Xbox Kinect. So it fires out light, which then it receives back and times how long it takes to get there. And so instead of just getting a single photograph, you get your photograph, and you get to know how far each pixel is away from the camera. So you can actually then, you take a picture like that, you don't just have an image, you've got, alright, so these points go like that, they're about 2 meters away, this point over here is only 30 centimeters away. And they also come built in with tracking as well, so as you walk around the room, the device knows it's walking around the room, so it's using the accelerometer as well as the camera and these depth images to keep track of itself. So from this you can then build 3D reconstructions of the room. So rather than where before we were broadly limited to a kind of a cuboid, we can now build an entirely really rich 3D reconstruction. Now, this is a huge area of growth. There are at least 3 major companies putting cameras out and desperate to get them into consumer devices. The big kind of limit at the moment is actually battery power. All these kind of devices are quite big or require external cameras. As they get smaller and sort of more power efficient, they become a huge application area, especially when it comes to, say, this sort of augmented reality with your HoloLens and all this kind of stuff. So we're looking at how we can take the data out of these systems and then understand that as well. So being able to say, okay, here's the structural room, this is where the walls are, this is how big the space is. One of our current things is actually to then integrate this directly into the web app you've seen. So as well as being just able to edit photographs, you'll be able to edit 3D scans of your rooms. You'll be able to visualize that with virtual reality and things like that. So there's loads of interesting applications. We actually, with an intern last year, we managed to line up all 3 new technologies. So we had the Google Tango making a scan of a room, and you could visualize that with an Oculus Rift on your head. And then you could move furniture around using a leap motion. I don't know if you've seen these. They're like hand trackers. So you hold your hands up and you can see your hands on the computer and you can pick things up. Because all the technologies in its infancy, it was a bit crap. But it was fun. We just loved it. So that's that. Thank you very much. I hope you enjoyed your time.